Hello, this tutorial is about combinations and permutations. First, factorial function will be introduced to you and then permutation and combination followed. Some exercise will be given in the end of these tutorials. Before learning combinations and permutation, we should first know what factorial function is. Using the simple explanation, factorial functions are mathematical concepts which means multiplying a series of descending numbers. N factorial means 1 times 2 times 3 until n, and the empirical equation is shown for the cases of n greater than 0. For n equal to 0, 0 factorial equals to 1. Here are two simple examples. 4 factorial is 4 times 3 times 2 times 1 and equals to 24. 7 factorial is similar and equal to 5040. There are some special cases for factorial functions. For example, 1 over 2 factorial is a half of square root pi. This is because factorial function is the gamma function. 1 over 2 factorial equals to gamma 1.5, and we can get a half of square root pi after integration. We're adding 1 to 1 over 2. 3 over 2 factorial is the multiple of 3 over 2 and 1 over 2 factorials, equaling to 3 over 4 square root pi. Therefore, we can easily calculate 5 over 2 factorial, 7 over 2 factorials, and so on. After having basic knowledge about factorial functions, we can move on to permutations. Permutation means the number of all possible arrangements of objects with orders and matters. For instance, the winners in all kinds of competitions, the problem of lighting up, and all kinds of order problems are permutations. From the graph below, we can see that all the outcomes contain same numbers of 1, 2, and 3, but they are in different orders, showing the importance of order in permutations. There are two cases about permutation, one without replacement and the other with replacement. For permutation without replacement, there are two cases too. When all objects are not repeated, choices are reduced each time after choosing an element from the population of n. For example, when we need to select 6 items from a population of 10 with orders, the possible choice for first selection is 10, and the second is 9, and so on, until 6 items is selected. Therefore, the possible arrangement are 10 times 9 times 8 times 7 times 6 times 5, which is 10 factorial over 4 factorials. So the empirical equation for permutation comes out n factorials over n minus r factorials, and there are 4 notations for permutation. Tree diagram is a useful graph to express permutation without replacement. First, in the top layers, 4 options can be selected if the population size is 4. The second layer will remain 3 elements being selected, and so on, forming 24 possible arrangements when we need to have a permutation of 4 different things from a size of 4. Here is 2 examples. First, when we need to select 5 from 8 different letters with orders, we have 8p5, which is equal to x factorial over 3 factorial, resulting in 6720 permutations. Then the second question is that how 6 customers can fit 4 staff. We should first calculate the first 4 customers being served, and it is 6p4. Then we calculate which 2 staff serve the remaining 2 customers, and it is 4p2. We multiply them and result in 4320 weight. For the second case of permutation without replacement, there are some subjects in population repeated, so some permutations are repeated too. In this case, the repeated time of all subjects are first known. For instance, first element repeats A times, second B times, third C times, and so on. The total number of selections is A plus B plus C till the end, equal to n. And the number of permutations is n factorial over A factorial times B factorial times C factorial, etc. Whereas A times B times C times all repeated times is larger than 1. Then we have an example to illustrate this case. A shiftwise fact to transmit some signal to others. Different permutations of facts means different kinds of messages. To calculate the number of messages, we should first calculate the total number of facts, which is the sum of all repeated facts, and it is 11 in this example. As we know the exact repeated number of each fact we can easily find out the number of message lengths. 11 factorial over 3 factorial times 4 factorial times 2 factorial times 2 factorial, resulting in 69,300 messages. After discussing permutation without replacement, we should talk about the cases with replacement. This is a very easy case. When we have n things in populations and we need to select out of them with replacement, we would be always n choice for each selection, so the number of permutation is n times r times n, which is exactly n to power r, where r is larger than 0. Let's talk about two examples. When we need to set a 6-digit password with replacement, the number of ways is exactly 10 to power 6, as 0 to 9 have 10 different options. Also, when we need to form a 4-lettered word from 4 different letters with replacement, the number of words being formed is 4 to power 4, which is 16. Come to the next section, combination. Combinations are all possible package of things which order is not important. Grouping and market buckets are the example of combinations. Some distribution, such as binomial distribution, also contains combination formula. From the graph, we can see that no element of two combinations are exactly the same. So combination do matter the elements, but not the order. Also, combinations are similar to permutation. It consists of two cases. For cases with replacement, combination formula is the reduced permutation formula by the number of ways in order, which is npr times 1 over r factorials, and the empirical equation is n factorial over r factorial times n minus r factorial. There are also four notations for the combinations, and the first one is more often used. Combination formula is also symmetric, since NCR is equal to its opposite, NCN minus R. Pascal triangle is a graph which is closely related to combination. We can see that these two graphs are the same and the value increases when it is moving down. The row number is the n values of combinations and the column number is the r value. This is very useful when we miss some combination question. These two examples help you to understand the application of combination. First, you need to select 4 friends from 7, so the number of groups formed is 7C4. And it is 35 ways. Similar to example 1, you need to select 3 beds from 10 to your trip. Since the order of pets is not important, we have just 10C3 ways to choose, resulting in 120 cases. For the combination with replacement, it is much more complicated. However, when we change the question to simple one, it is much easier to solve. We let circle to be the action of selecting the current element, and triangle to be the action of moving to the next element. For cases of n equal to 5, r equal to 3, we always observe that every combination contains 3 circles and 4 triangles, which is in the form of r plus n minus 1, resulting in a population size of n plus r minus 1. So we replace n in the original combination formula by n plus r minus 1. A new formula for combination with replacement is formed: n plus r minus 1 factorial over r factorial times n minus 1 factorial. Here is an example. You are choosing 2 dishes from 6 for your lunch set, and same dishes can be selected twice. So it is a combination problem with replacement. N equal to 6 and r equal to 2, so n plus r minus 1 is equal to 7. Putting into the combination formula, 7C2 is the number of ways to select the lunch set. Combinations are used widely, and 2 extensions are stated here. 2 common distributions, binomial distributions, and hypergeometric distribution, consist of combination formula 2. Both of them are discrete distributions, calculating the probability about success in n independent cases. For binomial distribution, NCR is used to find out all possible outcomes of success case in n experiments, while the probabilities of success number case in finite n experiments is calculated in hypergeometric distribution. For more details, please refer to the specific links. Lastly, there are 3 practice questions for permutation and combination. For the first question, you are required to form groups of two conditions, respectively. One is 3 freshmen, and one is equal number of different kinds of students. The second question is the number of 6-letter words with at least one repeated letter formed from 11 different letters, with and without considering the orders. And the last one is the rate of seat arrangement of 3 people to 8 seats with and without order. Part A of question 1 is easy. We just need to calculate the possible combination of freshmen from freshman group and the possible outcome of other 6 representatives from the other 2 groups, which is 7C3 times 9C6, which is equal to 2,940 ways. Part B is similar to Part A. We just need to divide 9 by 3 groups, and 3 representatives from each group is selected. So R is 3 for each group, and the multiplied is the answer. For question 2, to calculate the number of words with at least one repeated letter, we just need to calculate the total number of words formed by 6 letters and then minus those with no repeated letter. So for part A, we can easily get the equation 11 to power 6 minus 11p6. And for part B, we can get 16c6 minus 11c6. For question 3, part A, since the order of seats pending is important, and 8p3 should be the answer for this question, as 3 seats are selected from 8 with order. Since order no longer matters in part B, 8c3 is the answer as the combination of 3 seats from 8 is calculated. After having some practice, we have a brief summary before the end of this tutorial. To solve a problem, the first step is how we choose P or C for the question, which depend on the importance of the order. Permutations when order matters, and combination when order does not matter. After that, we should find out whether the elements can be replaced again, so as to find the suitable method for solving the questions. After watching this tutorial, I hope you have a basic knowledge of permutation and combination. Thank you, and here are the references.